Okay. So thank you, Rashid, for the introduction. So this is a part of my PhD thesis on human beatboxing, and this talk will be about voice production, and not so much about initiation or articulation. So next slide. Ooh. It works. Okay, so first thing, sorry for those who already know the video from my previous presentation. So this is an example of beatboxing. A linguistic approach of Proctor. So in his hemorrhage study on beatboxing in 2013, basically he says that beatboxing behaves like a combinatorial system, a discrete one. So you have a small set of primitives, like finite features or gestures, and then you have some coordinative structures that will combine these features or primitives. So while Proctor and colleagues looked at articulation that are similar to some that are found in phonological inventories, Blaylock and colleagues also on MRI study extended the corpus and also found mechanisms that are attested in phonological inventories, such as adjective in this case, but they also find some mechanisms that are not attested in phonological systems. So here, for example, you have an ingressive pulmonic trill. The first one is bilabial, and the other one is a retroflex ingressive trill. So the reason of this diversity of sonorities in the beatboxing system is yet to be explained. So basically, how the system structure itself. So what do we know about beatboxing? So first, the study and the PhD thesis of Annalisa Paroni. She just defended her thesis in September. And based on AIMER data, she found a reorganization of the articulatory activity and the emergence of new patterns of articulation. So from an aerodynamic point of view, with my data in my corpus, I found all the initiation mechanisms, meaning airflow can be generated in the lungs, the larynx, or the mouth, like pulmonic sound, ejective, glottalic, or implosive sounds, and also clicks. And the airflow can be either aggressive or ingressive. Plus, they combine these mechanisms with several articulatory mechanisms. And then you have, for example, the emergence of sounds such as ingressive pulmonic bilabial stop. Here you have an velar affricate, which is co-initiated by the larynx and the lungs, and you also have some aggressive clicks. These sounds do not appear in any phonological inventory, to my knowledge. So it has also been shown that the larynx and the pharynx can act independently or in a coordinated fashion. So we know a lot about articulation in human beatboxing, but there are no studies, to my knowledge, about voice production in human beatboxing. So voice production, voice is a very generic term that has different meanings. So sometimes it is used as a synonym for speech and talks about and refers more about the individual characteristics of someone's voice. It also can be a synonym to phonation, reduced to vocal fold phonation, and it's a bit reductive for a definition of voice. But lately, researchers prefer the use of voice quality because it makes a link between the acoustic and the perceptual cues. And then you can categorize different voice types. For example, to find characteristics of individual of their voice. Also, you can characterize or categorize pathological voice and typical voice. And of course, you can also categorize phonation types among linguistic systems or in a specific speaker community. So, for the anatomy of the epilarynx, so the number one is the epilaryngeal tube, and basically it's a tube in another tube that is the pharyngeal tube. So for the epilarynx, you have three planes. I mean, for the larynx, the glottic planes is not part of the epilarynx, sorry. So the glottic plane, you have the vocal fold, and they can move laterally to the midline of the glottis. Then you have the ventricular plane with the ventricular folds, and the space between the two planes is called the ventricle, Morgany ventricle. You can also compress this space. So basically, the ventricular folds have the same movement that the vocal folds, meaning they can move laterally toward the middle of the glottis. And then you have the aryepiglottic plane, which is the top of the epilarynx. Here would be like on top the apex of the epiglottis. And here you should have like the aerodynamics. And this plane does not move laterally, but in an anterior-posterior plane. And the epilarynx is both the ventricle and the laryngeal vestibule. So in the epilarynx, it starts with the ventricular plane and goes to the aryepiglottic plane. So this gives rise to the laryngeal articulator model, because similar to vowels and consonants categories, voice also has its own categories. So you have basic categories from Laver, and then updated by the laryngeal articulator model. So modal voice, falsetto, whisper, creak, harshness, breathiness. So here is the modal voice. So it's like the neutral state for phonation. And then you can have several configurations depending on the anterior-posterior constriction of the aerodynamics that are brought down on the root of the epiglottis, and the unconstricted epilarynx configuration that is more or less similar to what is illustrated with the modal voice. And then you have also varying degree of glottal aperture. So, for example, here you have the breath and the whisper. There is no voice. You can see clearly glottal aperture. The glottis is open. And for the whisper, you have an engagement of the aryepiglottic constrictor mechanisms. You see here the aerodynamics are not brought down on the root of the epiglottis. And for the whisper, you can see like an engagement of the aryepiglottic constrictor mechanisms. For breathy voice, here you have some vocal fold vibration, and you can see the same configuration for the unconstricted epilarynx between breath and breathy voice. But the difference is lie in the glottal aperture. And then you have an engagement of the aryepiglottic constrictor mechanism for whispery voice. Then for the creaky voices, you may have some ventricular voice. So here what you have is an adduction of the ventricular folds. So you cannot see anymore the vocal fold, these white structures. And then for creaky voice, you may have an engagement of the aryepiglottic constrictor mechanisms. Also, I would add this type of configuration, which is the aryepiglottic trills. So you have constricted epilarynx. You see the aerodynamics are brought down on the root of the epiglottis. And in the linguistic data, we do not have a corresponding configuration without constriction of the epilarynx. So, but maybe beatboxing uses this precise category, who knows? So turning now to a psychoacoustic model of voice. This model was built by Kreiman and colleagues in 2014. And contrary to the LAM, where the categories are based on articulation. Here you have more an acoustic and perceptual. I move a lot, sorry. Sorry, but the important thing is the PowerPoint presentation. So in this model, you have acoustic components that are relevant from the acoustic perspective and the perceptual perspective. So you have two components at the source. So not the filtered spectrum, but the source spectrum at the glottis. So two components for the source. The spectral slope, which is measured by measuring spectral tilts between the relative amplitude between harmonics in the low frequency region and the mid frequency region up to 5 kilohertz. Then you have the source noise component in the source with the harmonic to noise ratio, and it gives you an estimation of the relative amplitude between the harmonic structure and the aperiodic components from the noise in the source. So for example, for modal voice, you have regular voicing and the glottis is closed, so you don't have noise in the source and you have a high HNR. But in the case, for example, of a breathy voice, where you have the glottis do not fully closes, you would have much more noise in the source, so the HNR would lower. And then you can establish a distinction between phonation types. And then you have also F0 and F0 amplitude. And of course, because the modal voice also is integrating performance and the filter characteristic, you have to extract the transfer function from the speech signal. So Garolak in 2020 obtained an accurate classification of phonatory contrast in Mo, which is a pretty complex vocalic system, because this language, it is spoken in Namibia and Botswana, in Africa. It has 5 basic voice contrasts, like modal, nasalized, breathy, pharyngealized, and quicky. And you have 8 other voice contrasts that combines the basic contrasts. So you have a vocalic inventory with 5 vowels, E, E, A, O, U, but several contrasts depending of, for example, here nasalization, breathiness, quickiness, can also have like nasalized breathiness, and it's a very complex system. So if this model applies to such system, it's very complex. It should also work, well, it was my opinion, it should also work with complex systems such as human beatboxing, because these physiological and acoustic cues will not vary depending on whether you're speaking or beatboxing. So for the methodology, about first the setup. So first, we get the written consent of our participants for laryngoscopy and aerodynamic data acquisition. We also ask them to answer a questionnaire about their own knowledge of, for example, if they master more the imitation of drum sound, if they masters the production of voice effects, to see later in the analysis in the manuscript in my thesis, to know if inter-individual differences are linked to some factors like how many years have you been practicing beatboxing, are you practicing more electronic music or some drum music. So I have some metadata questionnaire. And then we describe the protocol for the participants. So it is 2 sessions of recordings. The first on top is the fibroscopic recordings. Then we had a break because it's a large experiment. And then came the aerodynamic recordings with the EVA 2 workstation. So the image at the bottom of the slide. So it allows to record acoustic signal, intraoral pressure in the pharyngeal cavity, also oral airflow and nasal airflow. So originally we have 5 participants, 1 male with the pilot subject, and then we have 2 females and 2 males. Unfortunately, we had some problem with the data of one female beatboxer, so we just excluded her because the data was absurd. I mean, we had no other choice. So there is a part, the main part of my thesis I will not explain today, but concerning voice effects, what I asked the beatboxers to do is do your thing. And like, what do you produce with the voice? What categories are there for voice production? And then I started to analyze the electronic sounds, so borrowed from electronic music, which is not from an instrument, but sound that come from computers. So synthetic, they are imitating synthetic musical sounds. And then we describe the corpus in terms of physiological cues of voice. And then we run a pilot study with the psychoacoustic model of voice. So first, as I said, we described the corpus and we used acoustic correlates that are based on the laryngeal articulator model. So from the articulatory categories. And first I went through the fibroscopic data to identify like some voice production that were very interesting to explain from a physiological point of view. Then I tried to match the two sessions, like matching the third base, for example, which is a category from the laryngoscopic data and the aerodynamic data. And then I proceeded to the description of the voice cues. And then we use Kreiman model and we use the inverse filtering technique. We extracted the transfer function and we estimated the glottal source. So inverse filtering very quickly. Here you have the output of the speech signal. You extract then the filter, you inverse the filter, and you subtract the inverse filter to the speech signal. And it gives you an estimation of the glottal source signal. And then you can plot it in a spectrum to analyze the periodic components, the aperiodic components, and whether the periodic components are regular or irregular. Physiological measures, so we extracted the F0 by cross-correlation, F1, F2, F3. We also measured oral airflow because it is correlated with glottal aperture. So if you have a wide open glottis, you have a lot of transglottal flow. But if you are producing like modal voice, your vocal folds are closed and transglottal airflow is lower. So after extracting these physiological measures, we inverse filtered the speech signal and we extracted several long-term average spectrums on a 50 millisecond window, because sometimes the voicing period exceeds the usual 25 millisecond window. So it's problematic. You cannot have the entire cycle on your spectrum. And then we measured the slope with spectral tilts and the harmonicity with H and R. For the results, so this will be the description of the corpus. So the third base, it was produced by a female beatboxer. Okay, so here you can see like the same configuration of ventricular voice. So you don't have a constricted epilarynx because the arytenoids are not on top of the epiglottis root. And you can clearly see this is not the vocal fold that are vibrating, but the ventricular folds. And two interesting things. The first part with an elevated larynx is produced with an aggressive airflow. And you can see a coupling between ventricular folds and vocal fold, meaning they oscillate as one pair of folds. And it is known to lower the F0, the average F0 by 1/3 or 2/3 approximately. And the second part was with the lower larynx. And then you don't have the coupling between vocal fold and ventricular fold because you are pulling down the larynx and it elongates the structure on the vertical axis. So you don't have the coupling between the vocal folds and the ventricular folds. So for the aerodynamic data, up there in green, you have the waveform. Then in cyan, you have the intraoral pressure, which equals 0 because there is no constriction in the oral tract, just like vowels. Then you have a positive airflow, meaning we have the aggressive variant of the third base. You have some slight oscillation on the nasal airflow, but it equals 0. And then you have the spectrogram. So for the frequential distribution of the energy on the spectrum, you can see clearly that there is a lot of energy below 2 kilohertz. But if you look also, you have some energy between 2 kilohertz and 4 kilohertz. So let's zoom in this region between 0 and 2 kilohertz, and you can see a very periodic structure. Here are the harmonics. And you have a very low at 0, 90 hertz, and it is produced by a female beatboxer. So this strategy of ventricular incursion allows her to lower sufficiently the F0 to imitate the low-pitched timbre of an electronic bass, like we heard in clubs, for example. So the inward throat bass, this is basically the same sound, but produced with an ingressive airflow. And it was not produced by a female speaker, but a beatboxer, sorry. They do not speak. I mean, yes, they do, but now they don't. So this is the ingressive variant of the third bass, and it was produced by a male beatboxer. So here you can see constricted epilarynx. So you have the aerodynamics that are brought down on the root of the epiglottis. And for the aerodynamic data, you can see on the waveform, it looks like pretty irregular. You have some small oscillation of the pressure around 0, but slightly negative. And here you have the oral airflow. So the 0 is just here, and you see the airflow is negative. So there is air coming in the lungs. Characteristics, it differs from the aggressive third bass because you have energy from 0 to 3 kilohertz, which is gradually decreasing. And you also have some energy between 6 kilohertz and 10 kilohertz that you can see in the spectrum. So here, the harmonic structure is pretty irregular. Like the first harmonics are well identified here in the spectrum, but from 600 hertz, you have a more irregular structure, which would mean you would have lower HNR compared to modal voice. Okay, then, the vibration bass. It was produced by a male beatboxer. So we are filling the gaps of the lamb model because here we have an unconstricted epilarynx and aryepiglottic false vibration. They are tensed. They are not vibrating on the root of the epiglottis. So if you look at the data, the glottis remains open, but you still have some oscillation that serves as a periodic source for phonation and for voice. So for the waveform, you see like it's periodic but very irregular. Then, which is interesting with this sound, is you have two parts. The first part has a lot of oral airflow, some nasal airflow. And the second part, you can see the airflow decreasing and nasal airflow increasing and intraoral pressure increasing. So what's going on? If intraoral pressure is increasing, it means there is a constriction occurring in the oral tract. So there is probably some movement going on in the vocal tract. Unfortunately, I don't have articulated data of the tongue. So this is an hypothesis. And you can see clearly the effects of increasing nasalization. So both parts of the so you have two on the spectrum. It's an LPC spectrum that shows the resonances. The straight line corresponds to the oral part and the dotted line to the nasalized part. But in fact, both parts are nasalized, but the second part has increased effect of velar-pharyngeal opening. Here you can see, for example, a big anti-resonance that cancels this formant just here on the spectrogram. Here you had a formant, and there you don't have anything. And you also have a larger anti-resonance between 4 kilohertz and 6 kilohertz that is canceling this resonance. It's pretty difficult because I'm comparing both nasalized sounds to see what is the oral configuration, because we know that nasalization has some strong effects on the resonances compared to like oral vowels in linguistic systems. So I would not dare to put a transcription of the vocalic timbre here, because it's pretty complicated. The inward bass produced by the same speaker that the vibration bass, and it's actually the same mechanism, but with an ingressive airflow. So what you see here is very fun indeed. So you don't have the epilaryngeal constriction, and what is going on is the tissue around the arytenoids, the interarytenoid tissues that are sucked in the open glottis. You still have the waveform like a periodic-like patterns with a lot of noise because the glottis is open, and it's very irregular because it's not the vocal fold that are vibrating on one another. So here you can see it's ingressive. This is the level of saturation, and unfortunately beatboxers have some powerful production mechanisms, and that saturates airflow. This is, for example, running speech values of airflow are 0.2, and here we are at -2 and +2. So we have saturation problem, and I don't know if we can increase the threshold for oral airflow and pressure. But anyway, for the acoustic cues, here you have a spectrum from 0 to 10 kilohertz, with energy decreasing gradually from 0 to 4 kilohertz. And then you have some energy here between 6 and 10 kilohertz. It looks like the same as the ingressive third bass. Maybe it is a cue of ingressive speech. It's a guess. I would have to run some further analysis to find the cue associated with aggressiveness, because beatboxers are able to distinguish without seeing, just by listening, whether a sound is ingressive or not. So importantly, maybe this region, there is something going on. So if we zoom at the region between 0 and 2 kilohertz, you can see that F0 amplitude is the highest harmonics, and then you have harmonics that are not strictly integers, meaning you can have an irregular structure of the harmonics. So last but not least, the chest bass. So the chest bass, this is the configuration. This is the epiglottis, the tongue root, the posterior pharyngeal wall, and the glottal plane is just behind the epiglottis. And thanks to Liz, we were able to see what is going on behind the epiglottis.
Essayez sur I un peu plus.
So here what you have is an engagement of the aryepiglottic constrictor mechanisms. So you can see the arytenoids are on the root of the epiglottis, and there is an association of the aryepiglottic fold, the left one, not the right one, but we don't see it on the video. So for the aerodynamic data and acoustic data, you can see clearly the periods on the waveform, which is very beautiful, in my opinion. You can have, here you have some pressure. My guess it's radiated subglottal pressure, but I'm not sure about that. I need to further look at the data. You have some oral airflow, and given the configuration, I would expect an even lower airflow, but not, meaning there probably is a lot of subglottal pressure to allow the air to force its way on this very, very, very tight larynx. Here you have energy only under 2 kilohertz. And if you zoom at on this region, you see a clear periodic pattern with harmonics and a very low F0 of 40 hertz. Okay, turning now to voice classification. So here you have all the configuration that are illustrated on both sides. So the two sounds that have the most elevated airflow are the inward bass with negative airflow and the vibration bass with the highest positive airflow. And it's not surprising because the glottis is open, so transglottal flow is higher. And then you have in this region the chest bass here on the left. And you can see that there is more airflow for the chest bass compared to the sample of modal voice, of spoken modal voice on the O vowel, that is slightly lower, and it comes from the same speaker. So the hypothesis of higher subglottal pressure for the air to force out these tightened larynx is plausible. Then you have the two third basses from the female speaker, just here with an unconstricted epilarynx, and then the third bass that is constricted, and it is produced by the same speaker that the chest bass and the modal voice. So the difference here between airflow, you would expect here, because you have a more constricted configuration, that you would have lower airflow. But once again, this beatboxer is the one who saturates my data. So he has a lot of pressure, subglottal interval pressure. And for me, it's the most plausible explanation for the higher oral airflow compared to the unconstricted ventricular voice. So for the F0 and the formants, so here you have a plot with the F0 at the bottom of the plot. Then you have F1 in green, F2 in blue, and F3 in purple. And each panel corresponds to one bass, one voice effect. So we have a clear distinction between F0. The highest F0 we measured was for modal voice. Then we have the third basses that has F0 around minus constricted, ventricular 60 hertz for the plus constricted third bass, and the last three sounds like under 500, 50 hertz, sorry, 50 hertz. So the vibration bass basically is 30 hertz, so the aryepiglottic folds are oscillating 30 times per second. The chest bass 40 hertz, and the inward bass it's like 50. You will also note that the F2 is under 1.8 kilohertz. Three beatboxers. So we have two male, one female, because when I try to match the sound with each other, it was very asymmetric. Yeah. Yeah, the female beatboxer is just here, the minus constricted, and she has a F0 of 90 hertz. So this is the the highest F0 after modal voice, but it's explainable because she's a female. Okay, so the F2 lies under 1.8 kilohertz, so you have like a dark timbre like posterior vowels. Okay, for the spectral tilts, so each panel corresponds to one bass, and each color measures one spectral tilt. So H1 minus H2. So these are the low frequency components in red and in green, and the purple and the blue color is related to mid frequencies in the source spectrum. So basically, you have spectral slopes that look like the one illustrated above each of basis sound, and we have two categories. In blue, categories that are falling pattern, and the other one you have like a positive tilt in the lowest frequency in H1 minus H2, and then it's decreasing. So spectral tilt itself does not allow to, for example, distinguish between chest bass, third bass, and vibration bass. But when you come with the harmonic to noise ratio, so you have a clear distinction between the voice effects. So on top, you have modal voice, which means this is the most periodic voicing. On the bottom, you have the less periodic voicing, and I showed you the spectrum in the 0 and 2 kilohertz region, the inward bass and the vibration bass with an open glottis as an irregular pattern of the harmonics. They were irregular, but still harmonics. So it's not surprising that they're at the bottom of the figure, because low HNR means there is a lot of noise in the source and it's not very periodic. And then you have the irregular phonation types, the chest bass here and both third bass. You can see that the chest bass is a little more periodic and regular than the third basses. And it may be due to the oscillation of the aryepiglottic fall. So to summarize, j'ai encore du temps? Ouais? Okay. So the categories of the laryngeal articulator model, sorry, and these categories are based on linguistic data. They also apply for human beatboxing production. So, and with our data, we found unusual phonatory behaviors, but we are also filling the gaps. So this was the figure from the beginning, and then we have the unconstricted epilarynx state of the aryepiglottic treating mechanism. And okay, so summarizing the production strategies of the beatboxers, you have in this database very different strategies. So for the source, you have regular harmonic structure, irregular harmonic structure, and also aperiodic components, that is noise, frication. And each of these source characteristics is not exclusive. In my corpus, they are combining irregular harmonics, which are called inharmonics or partial in a musical terminology. And you can also have a combination with regular harmonic structure and a periodic component if your glottis remains open. We have a varying range of S0 in the corpus that lies between 25 Hertz to 700 Hertz for male, 1500 Hertz for female. For bass sounds, you have low resonances with the formants. I'll show you that, for example, the second formant lies under 1.8. And you can also add further strategy like nasalization or pharyngalization to further modify the timbre. So this contrastive strategy are not very different from speech. The difference is the way the components at the source and in the filter are combined. So voice classification with Kreiman acoustic model of voice with the categories of the LAM model allows to strengthen both model actually. Because on one hand, you have the LAM model that lacks an acoustic link between the articulatory configuration and the acoustic output. And on the other hand, Kreiman model lacks articulatory categories to, because she relied mostly on the continuum between quickie, modal to breathy voice. That does not include, for example, the anterior posterior constriction of the aryepiglottic mechanism. So bringing these two models together results in a more accurate classification of voice, and we can establish a direct link between the physiological and the acoustical variables, such as the characteristics of the source spectrum, transfer function, articulatory settings, and also airflow. So for the perspective, I think this will constitute a strong base for the phonetic study of beatboxing voice, because it's very complex. And also, I think I might look afterwards toward more perceptual perspective to confirm whether our findings are perceptually relevant for the categories of the beatboxing basis sounds. So the problem with the corpus is it lacks symmetry and control. So we cannot compare the production between two subjects. So further studies on beatboxing voice production should build corpus that allows a direct comparison between subjects. And my guess is we would find a lot of interindividual differences. Like you would have more individual inventory than larger beatboxing sound inventory, depending on the anatomical capacities of the subject in the beatboxers. And also an interesting fact is to look at how beatboxing inventories and repertoire from the subject structure themselves, and whether or not they structure themselves the same way phonological inventories do on the scale of complexity, like simple articulation, elaborated articulation. As articulating, you had more contrast to complexify your categories. So it should be interesting. And thank you.